Hey everyone, welcome back to another MCAT Shemmassian workshop. Today we're exploring a high-yield Chem-Phys MCAT passage pertaining to Theranostic Pairs for nuclear medicine. We'll read the passage paragraph by paragraph, discuss any figures, and then we'll get to all of the questions complete with explanations. Let's get started. Before we jump into paragraph 1, we just want to point out that you can actually find over 4,000 MCAT practice questions on our MCAT question bank. Today, we're going to go over just 6 of them, but you can find the rest of them all on our website. Now let's jump into paragraph 1. Paragraph 1 states that Theranostics is a branch of nuclear medicine that administers combinations of radioactive compounds to simultaneously diagnose malignancies and administer therapies. These complementary isotopes are called Theranostic pairs. Theranostic pairs are often isotopes of the same element with low energy emission used for PET imaging and high energy emitting isotopes destroying nearby metastatic cells. And so for this paragraph, if we were to really reveal the highlights, we would see that we would highlight things like nuclear medicine, radioactive compounds, Theranostic pairs, same element, lower energy emissions, and higher energy emitting isotopes destroying nearby metastatic cells. The reason why we're highlighting those things would be because these highlights give us a couple of key things. They give us elements such as topics that will guide us in the main idea or concept that's going to be related to this paragraph. In this case, nuclear medicine and radioactive compounds. When you see that, that should put your mind into a very specific bucket. This paragraph is going to be about nuclear medicine, radioactive compounds, half-lives, isotopes, things like that. So we're highlighting those words. We're highlighting Theranostic pairs because that is a key word that seems unique to this passage, and it's probably going to keep getting repeated over and over again, but it's got its own definition. It's a word that we need to know for this passage. It's these pairs of isotopes that have these elements. It's the same element, but they have these different energy emissions. Low energy for PET imaging, which is a technique that we should know, and high energy for emitting isotopes. And the high energy helps with destroying nearby metastatic cells. Metastatic cells being a term that we should walk into this passage knowing. So when we're highlighting things, we want to be thinking about main ideas, concepts that are pertinent to the passage, like very big overarching concepts or topics, as well as organization. What things are in this paragraph that likely will not show up anywhere else. So in this paragraph, we highlighted a lot of concepts and terms and topics, things like that. Now let's jump into paragraph 2. Paragraph 2 states that lanthanum-133 and 135 has been identified as a theranostic pair that is preferred over lanthanum-132 and 135 due to the reduced positron and gamma emissions resulting from the heavier isotope pair. Researchers discover a high-yield production pathway to obtain suitable quantities of lanthanum-133 and 135 by irradiating pellets of naturally occurring barium, which will be written as natural barium, with 22 million electron-volt proton beams generated by a cyclotron. The resulting nuclear reaction cross-sections are shown in Figure 1. And so for this paragraph, if we were to reveal the highlights, you would see that we'd highlight things like lanthanum-133 and 135, there being a theranostic pair, that it's preferred, and that it has reduced positron and gamma emissions, and it results from a heavier isotope pair. We also highlight something like barium and the 22 million electron proton volts. So we would highlight those things. And again, we're highlighting things because they're probably going to help us with the question, or at least the understanding of this paragraph. So we have our pairs that were brought down from paragraph 1. We know what type of isotope pair we're talking about, 133 and 135. We know that those are preferred. We know that they're preferred for what reason? Because it's reduced positron and gamma emissions. That reduced emission is a result of heavier isotope pairs. So you know if something's heavier, that it's a little bit better, and it's better because of the reduced positron and gamma emissions. It's the first time we talk about something like barium, so organization-wise it's important. And then we have a number like 22 MeV, which could, it could be involved in an equation, or it could be involved with a question, or some value that's in the figure. It's just a very specific number, and we always want to be collecting numbers if it seems pertinent. So that's paragraph 2. Now let's look at figure 1. Figure 1 is titled Nuclear Reaction Cross-Sections for the Production of 13X Lanthanum from Natural Barium. So with this graph, you can see that it's a bit complicated of a figure, right? We've got a lot of different variables here, a lot of different characteristics, a lot of different lines, and it's just complicated to read and understand the trends here. So for a figure like this, I would spend very, very small amount of time looking at this figure. I'd focus mainly on what are the titles, what are the axes, and that's about it. I'm just focusing on organization. What information shows up in this paragraph, or in this figure, sorry. And in this figure, what we'll see is it talks about beam energy, it talks about cross sections, and we have variations of barium and variations of lanthanum. And we see the numbers like 22 MeV show up again. So that's about it on this figure. If we get a question specific to this figure, we could always come back. So let's look at paragraph number 3. Paragraph number 3 states that the produced 13X lanthanum isotopes were further characterized through radio labeling with DOTA and Macropa chelators and radio TLC. That unreacted 133 and 135 lanthanum migrated towards the solvent front, while the 133 and 135 lanthanum Macropa complex remained at the TLC baseline. And so if we were to reveal the highlights for this paragraph, we would see that we would highlight things like 13X lanthanum isotopes. We would highlight that it's characterized with different techniques like DOTA and radio TLC. We'd also see like the main takeaway of this paragraph seems to be that unreacted lanthanum migrated towards the solvent front and the Macropa complex remained at the TLC baseline. That's going to be important because if you know what a TLC plate or the results of a TLC plate analysis looks like, understanding what something means, the information behind something moving towards the solvent front versus remaining at the TLC baseline tells you a lot about each one of those. And so that right there would be the takeaway of paragraph 3. Now let's jump into paragraph 4. Paragraph 4 states that the efficacy of radioisotopes in PET imaging is strictly dependent on the decay activity of the radiotracers. Several common decay characteristics of isotopes used in PET are listed in figure 2. And so if we were to reveal the highlights here, we would see that the things we would highlight are efficacy of radioisotopes, strictly dependent on the decay activity of radiotracers. Really simple paragraph, very short paragraph, but it's got a very clear takeaway sentence. And when we're looking at that sentence, it's showing you the relationship of one thing to another. And so when we're going into figure 2, we know what information is going to be in it. We're going to look at different decay characteristics of isotopes. So that right there would be paragraph 4. Now let's jump into figure number 2. Figure number 2 states that the title is Decay Characteristics of Isotopes Commonly Used in PET Imaging. When we're looking at this table, you can see that again, there's a lot of variables here, right? We got lanthanum 133, 132, fluorine, we got a bunch of different isotopes, we got half-lives, we got mean positron energy again. So there's a lot of different isotopes, a lot of different variables, a lot of different characteristics. Instead of trying to look here for trends and information, what we should be focusing in on is organization. Not really on understanding what the graph or the table is trying to show you, but focus more on organization. What key things show up in this figure? What shows up is isotopes in PET imaging, different types of isotopes, lanthanum, fluorine, right? Like we got different types of isotopes and we have different half-lives and we have different energy levels. The key thing here is like sometimes we're given something like half-life. Half-life is in either hours or minutes. Hours and minutes is the same thing as time. So as you're getting information, you almost want to like unravel it a little bit in your head and be like, I'm given half-life. Half-life is in hours. Hours is the same thing as minutes. Minutes is the same thing as seconds. Seconds is the same thing as time. And so that helps out because sometimes you use an equation where the equation has t in it. And you might be thinking, there was nowhere at all in the passage that talked about different times. But it does. In this passage, in this figure, it talks about half-life, but in terms of different units. So when you're seeing math, numbers, variables, think about all the different things. Think about equations, think about units, think about variables, think about how they're all related and how they can be converted into different things. You want to unravel it a little bit, just in case you need it for future questions. So hopefully that passage breakdown felt good so far. We're going to head into the questions now. But before that, I'd like to just mention that if you're looking for more information on MCAT buzzwords, do check out the comprehensive list of high-yield key terms listed at the bottom of each content unit in our MCAT Premium Content Hub. Again, that can be found on our website. Now let's jump into question number 1. Question number 1 states, which of the following reaction pathways describes a major production pathway of lanthanum that is specific to this experiment? And what we always have done is that we look at answer options and we think about different similarities, pairs, and differences. And so when you're looking at these answer options, you'll see that as you look down the barium column, like if you imagine these things as columns, you'll see that all of them have barium and 1 proton on the left side. The thing that makes it different is the type of barium. Is it barium 132? Is it barium 135? Is it barium 134 or barium 137? If we look at the right side, we've got 2 columns. We've got the lanthanum and the number of neutrons. And so we'll see that there's another difference. Is it lanthanum 132 or 133 or 133 or 135? If we're looking at the neutrons, is it either 1 neutron, 3 neutrons, 2 neutrons, or 3 neutrons? So a good way of doing these questions is looking for things that, like, if they're all different, you only got to find one thing that's correct. What if you know that it's got to be barium 132 plus 1 neutron? What if you know that it's got to be lanthanum 132 plus 3 neutrons? Like, if you can find a specific part of an answer option that is certainly correct, you know the rest of it's going to be correct if everything about these answer options is different. So in this case, we want to be thinking about it as this. So this particular cyclotron, like when we were looking at figure 1, that cyclotron produces isotopes through exchange reactions. And figure 1 states that there was 2 major pathways that are highly likely to take place when beam energy is 22 MeV. And one of those pathways was denoted by a black diamond, and the other pathway was denoted by that red cross. So the reaction denoted by the red cross is noted as barium 134 and lanthanum 133. And so that's showing that the addition of 1 proton and the removal of 2 neutrons from that barium 134 will likely produce lanthanum 133. And so because of that, that points to likely answer option C, that at 22 MeV, that cyclotron promotes this reaction where barium 134 absorbs that 1 proton and loses 2 neutrons. So let's jump into question number 2 now, and it states that a patient receiving a PET scan is injected with 18 fluoride radioactive glucose before the test. Approximately how much time must elapse before less than 5% of the original radio-labeled isotope is present in the bloodstream? And so with this question, you can see that it's talking about an amount of the original radio-labeled isotope that would remain present. And so when you get information like that, that sounds a lot like half-lives. Another thing that should seem pretty pertinent is that it talks about fluorine-18. Where else in the passage did we talk about fluorine-18? Only one place, and that place would be figure 2. And so when we're doing this question, we're just thinking about how many half-lives would lead to less than 5%. And so when you have pretty much after each half-life, the amount is reduced by half. That's what a half-life is. So after 2 hours, in the case of fluorine-18, right, so 110 minutes, so after about 2 hours, 50% remains. After 4 hours, about 25% remains. After about 6 hours, about 12% remains. And after about 8 hours, about 6% remains. So that 6% remaining that's just above 5%. So by 8 hours, you have about less than 5% left. And so for that reason, answer option C would be a good option. Question number 3 states, as compared to naturally occurring barium, isotopes of lanthanum are Roman numeral 1, larger in atomic radius, 2, more electronegative, 3, less favorably ionized, and 4, more likely to form covalent compounds. And so when we're looking at this question, you can see that almost all of these answer options have to do with periodic table trends. And so we just need to know those trends. So when we're going through the statements one by one, the atomic radius, that is decreasing as you go right and as you go up. So lanthanum would have a smaller atomic radius than barium. So for that reason, statement 1 is false. When we're looking at electronegativity increases as you go right and as you go up. So statement 2 would be true. When you're looking at ionization energy, that also increases as you go right and as you go up. And so that indicates that it's less favorable for lanthanum to ionize, which makes statement 3 true. And when we're looking at statement 4, lanthanum has 3 electrons in its valence shell. And so indicating that it is more likely to form covalent compounds than ionize and form ionic compounds. So for that reason, we're going to have to probably go with answer option D for this one. So let's jump into question number 4. And that one states, which of the following sets of quantum numbers describes an electron located in the valence shell of barium-137? And so when we're looking at this question, we got to be thinking about barium-137 and the electrons in its valence shell. So what do we know about barium? We know that barium has an atomic number 57, that it's located in period 6. The second quantum number describes the shape of the atomic orbital. And in the case of this barium, it's in the s orbital, which that's going to give the second quantum number a 0. The third quantum number is going to range between a negative and a positive value. And so that has to be a 0. It can range from negative to positive. And the fourth quantum number represents its electron spin, which is either a positive 1/2 or a negative 1/2, with electrons of opposite spin forming a pair. And so when we're looking at this answer options, right, like we want to just be thinking, how easy would it have been to find this answer? And so you look at these different quantum numbers and you think about what's the same and what's different. A and B have 6 as their first quantum number, and C and D have 2 as their first quantum number. So if you just know that first quantum number, you're already down to 2 answer options. And just doing little tricks like that help you narrow down your answer options so quickly. So for this case, the answer option was going to have to be B. Now let's jump into question number 5. Question number 5 states that lanthanum-133 is the preferred theranostic isotope due to its what? And again, with this question, you want to be thinking about what's the pairs here. And if you look at the answer options, you'll see a pretty clear pair right away. You'll see that B and C both have to do with lower emission rates. And so that is not to say that if you see a pair in the answer options, that it is always the answer, that the answer is going to have to be between B and C. That's not what we're saying. We're saying that the answer could likely be B or C because we have 2 answer options that are very similar, making them hard to tell apart, making them great options to be stuck between if you're a test maker. If you know that this has to do with lower emission rates, you're down to B and C, so you're down to 50-50. If you know that this has nothing to do with emission rates or lower emission rates, then you know that B and C are wrong, so you're still down to 50-50. You're down to A and D. So looking at pairs helps you narrow things down fast, whether those pairs are right or whether those pairs are wrong. And so in this case, you want to be thinking about, where did we talk about lanthanum-133 or a preferred theranostic probe? And that was in one of the paragraphs. And so that passage stated that the heavier isotopal lanthanum emits fewer positron and gamma emissions. And gamma radiation is this form of ionizing radiation that can interact with biomolecules like DNA, and that can severely damage health tissue. And so for that reason, answer option B is going to be the correct one. And on to the last question, question number 6. Question number 6 states, which of the following reactions describes the predominant activity of lanthanum-133 during a positron emission tomography scan? And with this one, again, you'll see that we're going to look for pairs and differences. We see that they all have to do with lanthanum-133, that it's decaying into something else. Is it decaying into barium? Is it decaying into cerium? Is it decaying into lanthanum? Or is it decaying into cesium-129? With that being said, we also have something else that's different. Is it a plus beta particle? Is it plus beta minus particle? Is it a gamma ray? Or is it an alpha particle? And let's just remember, right? When we're looking at these answer options, we can look for one thing that's correct. We can also look for things that are wrong. So in this case, we're looking at a question that's referring to PET tomography. And that scan, a PET scan, has to do with beta plus particles. That being known, we can immediately cross off certain answer options because they don't have anything to do with PET scans. So D is out. PET scans typically have to do with beta plus particles. So PET scans have to do with the isotopes that undergo beta plus decay, which means that a proton in the nucleus is converted to a neutron while releasing a positron. And that's exactly what answer option A is saying. So you can use pairs, similarities, and differences to narrow it down to two options. And you can narrow it down to two options that are right or two options that are wrong. If they're wrong, you cross them off. If they're right, you keep them. You can also use similarities, pairs, and differences to just find one little thing wrong with any answer option. If you can find anything wrong with an answer option, the whole thing's wrong. So we know that this has to do with the PET scan. Cross off anything that has nothing to do with beta particles. So beta plus decay. And there's only one answer option really there that has to do with beta plus decay. That's answer option A. And so for that reason, we go with A for question number 6. And with that, it looks like we survived to the end of the passage. These radioactive and nuclear passages are always a ton of fun, aren't they? So thanks for joining. We hope that this walkthrough is helpful in your MCAT journey. If you're looking for more practice resources, you can visit our MCAT question bank or premium content hub for thousands of sample problems. Or if you want a more personalized approach, our MCAT experts provide a one-on-one tutoring atmosphere, as well as individualized study schedules and test-taking strategies that go a step further than just content review. Check out our website to learn more, or feel free to drop a comment here with any questions you may have. Happy studying!